Okay, so I was asked to make a quick review on geometric and arithmetic sequence formulas, so explicit and recursive. My goal is to make this pretty quick and straightforward. So we're going to review arithmetic and geometric sequences and then two formulas associated with those, so recursive as well as explicit. Okay, so let's start with arithmetic. So arithmetic is where um, we are adding to get from one term to the next. So um, the example that we'll use is, let's see here, 3, 7, 11, 15, so on and so forth, right? So to get from 3 to 7, we add 4. From 7 to 11, we add 4. 11 to 15, add 4, and that same pattern is going to continue on, right? So that 4 that we're adding each time, that's what we call the common difference. Or we just call it D. Okay, so D is equal to 4. And that's nice to know because it is something that we're going to use in both formulas, right? So if we're going to come up with a formula, it's probably nice to know how we're getting from one term to the next, whether that's adding or multiplying or something like that. So we're always going to look for what that change is and then incorporate that into a formula somehow. A few other things. Our first term in the sequence is going to be A1, okay? A subscript 1. So although the 1 is telling me is where that term ends up in the sequence, right? And so our A1 term is going to be 3. It's that first term in the sequence. It's where the sequence technically starts, okay? And then we use the difference to get from A1 to A2, which is our second term, A3, which is the third, so on and so forth, right? And all the way out to what we call the AN term, which is just some term that we haven't found yet. But the N is just representing what number term that is in the sequence, right? So our 15th term would be A sub 15. Okay. Yeah. So those are some of our kind of important terminologies that we'll use. The last important thing is just that we like to label each term, right? So that's what we'll call the N. So for our first term here, N equals 1, N equals 2, N equals 3, N equals 4, and all of that links to, so first term, N equals 1 term is A1, the N equals 2 term is A2, so on and so forth. So you can think about N is kind of like X, and AN is kind of like Y, right? So I put in X, I get out Y. We could maybe put that in a table format, right? So in this case, my term number is 1, 2, 3, 4, and I'm getting out. If I put in the N equals 1, then I get out A1, which is 3. If I put in 2, then my formula that we're going to work towards making should give me out A2, which would be 7, 11, and 15. So A1. Okay. Now, to get from A1 to A2, we added 4 once, right? To get from A1 to A3, I'm adding 4 twice. To get from A1 to A4, I'm adding 4 3 times, right? So hopefully you're starting to see a pattern. To get any number of terms, I'm adding my common difference n minus 1 times. So n being the term number, n minus 1 times. So And that is going to be the key to our formula, right? Because if you think about it kind of like a line, we talked about linear functions, that d is going to be our slope, right? And our n minus 1 is just telling us where we're happening on the graph. So we can start to build that formula to get to a certain term. I want to add d n minus 1 times, right? But if I just add d n minus 1 times, then I'm just going to get multiples of 4. So my second term would be, it'd be 4, 8, 12. Obviously, that's not right. We have to think about where we're starting. And our a1 term was 3. So we want to start at that a1 term, a1, plus however many times we add it. And that's going to give us out our an term. And that's what we call the explicit formula. So for our case here, an is equal to our first term, which is 3, plus our common difference, which is 4, and we're doing that n minus 1 times, right? And if we wanted to, something that the SAT frequently asks for you to do is to simplify that, and all that means is that we're multiplying out this binomial here, right? So I do 4 times n, 4 times negative 1, okay? And so we'd have 3 plus 4 n and minus 4, and then we combine like terms and should get out 3, or sorry, that's my bad. So we take 3 plus negative 4, which would leave us with negative 1 plus 4n. Okay? Now, both this formula and this formula are correct formulas. They're both explicit formulas. They're the same thing. They're just two different ways of writing it, right? So if you were asked to simplify, then you would want to give this bottom one. If they just asked for, I don't know, the 15th term, then you just build that first formula and use it. There's no reason to take any time simplifying it, right? That's the explicit formula. The recursive formula, is a formula that takes the previous term to get to the next. So to get my 10th term, I need to have the 9th term. And to get the 9th term, I have to have the 8th term. And to get the 8th term, I have to have the 7th term, right? So all the way back to the first term. Now, the nice thing about this is that in things like computer coding, you can build these formulas that take your previous value, it stores it, and then in this case, we would add 4 to it, right? So if you knew what your 18th value was, then you could store that value, add 4 to it, and you get the 19th value, which is far easier than just plugging in 19 to the formula and simplifying that. The downside is that to get any term, we have to have the previous term, right? So having these two different formulas allows us to cover our bases and kind of approach sequences in a way that would be beneficial to us for any certain scenario, right? So if you're going to be asked to find different random terms, then having the explicit formula is going to be pretty useful. But if you're asked to give me, okay, give me the next 50 terms in the sequence, it's going to be a lot easier to just say, okay, add 4, okay, add 4, okay, add 4, than it is going to be to plug in the plug in 47, okay, plug in 48, okay, plug in 49, okay, plug in 50. That's going to take a lot longer, right? So what our recursive formula does is it takes our first, it takes, if we want to find an, so if we want to find the 10th term, then what we need is the 9th term, the term before it, the n minus 1 term, okay? And all that n minus 1 is doing is indexing. It's telling us which term we want. It's not something that we are adding or subtracting or multiplying. It doesn't do anything, right? And then we're adding the common difference. So in this case, that was 4. So for our previous example here, our specific example would be to get an, then I want the previous term, and since I know I'm going up by 4 every time, I'm going to add 4. So the only thing that's really going to change is what your common difference is based on whatever that term is, right? And so this is our recursive formula. Okay, so we've got 2 different formulas, both for the same sequence, giving us 2 different things. Okay, so there's the overview. Let's look quickly at geometric sequences. So the geometric sequence that we'll do will be, we'll make it pretty easy. Okay, so it'll be 2, 4, 8, 16, 32. Right, so if we tried to look at this as an arithmetic sequence, plus 2, plus 4, plus 8, plus 16, that's not working. Okay, well, if arithmetic doesn't work, then let's go try geometric. Okay, and so let's see what we can come up with with geometric. Instead, let me multiply. So to get from 2 to 4, I multiply by 2. From 4 to 8, multiply by 2. 8 to 16, so let's multiply. 16 to 32, multiply by 2, and presumably so on and so forth. Right, so we've found the pattern. We've found what we previously called the common difference, but the differences this time were not differences indicating like the difference between 2 numbers on a number line. So calling it the common difference wouldn't quite be correct. Instead, we call this in a geometric sequence the common ratio, or R. So the common ratio for this problem is we're multiplying by 2 every time, so R is equal to 2. Right? Now, to get the explicit formula, remember, I've got kind of a table set up where if I plug in n, I want to get out that term number. So if I plug in 15, I want to get out the 15th term. If I want to get the an term, then I want to plug in n. Right? That's all that is just a generalized version. Okay? So to get an, I take the first term in the sequence. So we talked about it. That's all that is if you look at the sequence, it's your first term that you're given. That's in this case, a1 is 2. That would be our first term. Okay. And then we want to multiply that by our common ratio. But we have to multiply it by however many times we're using the common ratio. Right? So if we look to get from 2 to 4, I multiply by 2 once. To get from 2 to 8, I multiply by 2 twice. To get to the 4th term, I multiply by 2 3 times. So same as last time, we're using our common ratio instead of our common difference, n minus 1 times. All that's saying is to get to the 4th term, I'm using it 3 times. To get to the 5th term, I'm using it 4 times. But if we just multiply r by n minus 1, that indicates that we're adding it multiple times. Instead, we have to raise r to the n minus 1 power. Well, that's not very easy to see. N minus 1. All right, and so this is what we call the explicit formula for geometric. Okay, so for this specific example, to find the an term, we want the first term, which is 2, times our common ratio, which is also 2, and we raise that to the n minus 1 power. That's not going to change. that is our explicit formula for our given sequence. If you wanted to, and you felt pretty good with your algebra and exponent rules, whoa, that was weird. You could simplify that to be an is equal to 2 to the n. That I don't expect you to know or be able to do very well, but if you can and notice that, that's something that could potentially save you time in the long run, right? So that's our explicit formula. Last one we want to talk about is recursive. Right, and so recall that recursive takes the previous value, increments it to get the next value. So to get an, you would take the term before it, an minus 1, and instead of adding, right, because this time we're multiplying every time, well, then if we're multiplying every time, then we multiply by the common ratio. So in this specific example, we would take the n minus 1 term and multiply it by 2. And that would be our recursive formula for this sequence. Right, so between these two formulas, you should be able to do a lot of different things in terms of finding missing values within our sequence, right? So at the bottom of this, I'm going to make a little table with the formulas so that you guys can have the video paused up on your screen and have those to kind of reference. This applies to our last two, what's the word I'm looking for? The last two lessons from last week. So if you're still working on those, you still need help, these videos will be available to you. And if you need to look at just the formulas, you can pause at the end and reference those. Okay, so I'm not going to talk anymore, but that is where they will be.